Hello guys, I'm Mayank and this is a demo of PyAono repository which went live on GitHub fairly recently. If you're interested in looking at it, you can head on to OpenMind's GitHub page and you can find this repository there. So without wasting time, let's just get right into the stuff. Uh, First, I'll be showing you the the basic. First, I'll be showing you what the present API is capable of doing. We have wrapped all the CPP code in Python, so this is how you can access the API in Python. As you can see, this party init, this function is used to allocate a stack uh, separately for all the data that will generated during this processing. And you destroy the stack by calling party close. Uh, Now this this line here, this is used to generate the keys. Uh, I've just hard coded some parameters here for the sake of this demo. First, we need to generate ciphertext because we have to operate in ciphertext. This is what this demo is about. So here I've created three ciphertexts. The first ciphertext encrypts the number 4, the second ciphertext encrypts the number 5, and the third ciphertext encrypts the number 6. What this 64 here is that uh, as far as Aono encryption is concerned, each input, each message, each plain text has to be a matrix which is 1 cross L. Now this L is a parameter which I have taken to be 64 here. So what this first ciphertext is that it is an encryption of a matrix which has dimension 1 cross 64 and has 4s at all the places. So it is like 4 4 4 4 4 64 times, and so on, the second one and the third one. Now let me show you how this thing works. Suppose you want to add two numbers 4 and 5, but you want to do them with their ciphertext. So first you take you encrypt the number 4, you encrypt the number 5, and now you can just do ct1 plus ct2, which will do a homomorphic addition of both the numbers. So you should get a homomorphic. You should get an encrypted 9 here, since I'm adding 4 and 5, and this thing here, it decrypts this encrypted 9 using the secret key. So you see that we get 9s. Since I told you that a message is a matrix of dimension 1 cross 64, so you'll see 64 9s here. Now we proceed on to a demo of subtraction. You see that when I subtract CT2 from CT1, which is an encryption of 5 subtracted from an encryption of 4, you should get an encryption of 1, which when decrypted gives you 64 ones. Moving on to the multiplication demo. Now this is somewhat complex to understand. You might be thinking that how do all this gibberish come from? It was fine to have 64 20s, but these don't look like 64 20s. These are more 20s. This is actually because the way Aono homomorphic encryption works is that it takes when it does homomorphic multiplication, you don't get a message that is of size 1 cross L or 1 cross 64 in this example. You get a matrix of size L cross L, that's 64 cross 64. So you'll basically be seeing 64 square 20s here, which is exactly the case. This is what prevents this homomorphic encryption scheme to support more than one multiplications, or even support an addition over a multiplicated ciphertext, because a multiplicatively operated ciphertext here looks very different from what a conventional addition operator should expect. It should expect that it is getting two ciphertexts which are 1 cross L, 1 cross L both, and it just adds both of them. but here you have a ciphertext that's L cross L. So this is a limitation of this encryption. So if you do a multiplication in this encryption, you cannot operate on the ciphertext further. You have to decrypt it. But you can do a lot of additions and then finally do a multiplication. That will definitely work. And that's the next demo that I show. Now, yeah. Now you see that I've done some nested addition and multiplication here. I'm first adding 4 and 5, which is 9. Then I'm adding 5 to it, which is 14. And then I'm multiplying it with 6, which is 64. Which is, sorry, 84. So you can see that the API now supports nested addition, multiplications, additions, simple additions, multiplications, and subtractions. Now let me show you how a ciphertext in this encryption scheme looks like. You might be thinking, what is all this rubbish? This is actually how the errors add up and they make the message obfuscated so that an adversary cannot look what the message actually is. You can see that this is actually a structure, a modulo structure. What it does is that this is Q. Q defines a ciphertext space modulus, and this is what the ciphertext actually looks like. This looks very different from what you'd expect a plain text to look like, because we have added some noise to it so that an adversary cannot just see the ciphertext and guess what the message actually had been. So this ends up my demo about PyAono. I'll be closing this thing up. Now I'll be showing you one of the unique features of this encryption scheme, and that is it supports key rotation. What key rotation essentially does is that you can have a secret key, a person who has a secret key, and this person, he can generate a set of public keys, which when used in a particular order can actually change the ciphertext as you go along the way, and when you finally decrypt it with the secret key, you get the correct result. So this helps very much when you want to distribute the power of decryption across a lot of people. You can just send them their respective public keys, and they'll not be able to see someone else's data because they don't have the secret key. Only only one party has a secret key. Okay, now let me show you. Yes. As you can see, this is what error terms generally look like. This is an example error term. This is also of size 1 cross L. You see that these are all just random data. This is what encrypts our messages and makes them secure against an adversary. Now, as I was just talking about key rotation, just look at these two components here. The first one is an example ciphertext that was an example ciphertext before key rotation happened. So you can see that it has 966 in its beginning. Now when I rotated the keys, I got a new pair of keys, and when I used those keys to change the ciphertext from C1 to another one, I should get a fairly different ciphertext, and that's the case indeed. You can see that this one has 1442 in its beginning. So this is how key rotation works. It just changes the ciphertext from one form to the another, so that if the first one was correctly decrypted with one set of keys, the second one will be correctly decrypted with an incrementally rotated set of keys. You can see that even after key rotation, when we use the secret key, we get the correct result. We get 64 twos here, and when we go up, we see that the actual message was also 64 twos. Yeah. So that's how key rotation works. We'll be rolling out key rotation in the PyAono GitHub repo very soon. So just stay tuned for that. And if there's anyone who wants to contribute to this API development that is happening for the PyAsh, PyBV and PyAono GitHub repositories, then you can just contact me on Slack, or you can send me an email. Thank you.